So, in the last class, we started the integer linear programming problem, where the decision variables are the integers and they take the positive values. We have done the Gomory's cutting plane method. If you remember, we have told in the last class that IPP problems can be solved by two ways. One is Gomoryan cutting plane method, where whenever you have one variable, decision variable in the basis whose value is non-integer, you are adding one constant and you are adding one Gomoryan slack variable to remove that particular decision variable from the basis. So, that we have seen in the last class. Today, in this class, we will discuss the branch and bound method for solving the IPP. It is similar to this earlier one. There is a basic difference in branch and bound method. In branch and bound method, at first we try to find the solution and we check that which variables in the basis has non-integer values. From there, we try to find out the upper bound and lower bound of the problem, and then we divide the original problem into two subproblems by adding two more constants using the lower bound and using the upper bound of the problem. So, that we are doing it. So, let us see what the branch and bound method uses. In branch and bound method, suppose you have a problem, maximize z equals c x subject to a x equals b, x j greater than equals 0, and this is integers. Now, if x j is not an integer, in that case I can write down x j equals w j plus f j, where w j is the integer part and f j is the fractional part, where f j lies between 0 and 1 obviously. So, you have the problem, original problem, maximize z equals c x subject to a x equals b, x j greater than equals 0. If x j is not an integer, in that case we are writing x j equals w j plus f j form, where w j is integer part of the variable and f j, which lies between 0 and 1, is the fractional part of the problem. Now, any feasible integer solution of the problem, if you take any, it will must satisfy any one of these two conditions. I think it is fine. X j less than equals w j or x j greater than equals w j plus 1, because the bound it will be either exactly less than equals w j or it will be plus 1, since your f j is the fractional part whose value lies between 0 and 1. So, for any feasible integer solution of the problem, it must satisfy any one of these two constants, x j less than equals w j or x j greater than equals w j. So, basically what we are doing, since your x j is less than equals w j or x j greater than equals w j, so we are dividing this original problem into two subproblems. In one subproblem, we will include the new constant x j less than equals w j, and in the another subproblem, we will include the other inequality condition x j greater than equals w j plus 1. Or in other sense, I can reformulate two subproblems like this. One I am telling as SP1, where we are telling maximize z equals c x subject to a x equals b, x j greater than equals w j plus 1 and integer. So, one condition we are writing here, x j greater than equals w j plus 1, and obviously all x j will be integer, and the subproblem 2, which we are denoting as SP2. This we are writing as maximize z equals c x subject to a x equals b along with 0 less than equals x j less than equals w j, and x j's are integer. So, whenever I am getting the lower bound and the upper bound of an non-integer variable in the basis, from there I am making two conditions, x j less than equals w j and xj greater than equals wj plus 1, and from there we are formulating two subproblems like this sp1 and sp2. Now, the solution having larger objective function value will be the required optimal solution. So, there are some possibilities. One case is both the problems sp1 and sp2 has optimal solution and they satisfy the feasibility condition, that is you are getting the integer solution for both the problems sp1 and sp2. In that situation, the solution having larger objective function value will be the required optimal solution. Now, if any subproblem has non-integer variable, if any one of these two subproblem has non-integer variable, then again it should be partitioned for that. That means, you have the original problem SP. Once you have the original problem, and for this particular problem, if the optimal solution contains non-integer values for the basis variable, divide it into two subproblems sp1 and sp2. One will contain the lower bound constant, the other one will contain the upper bound constant. Then again if required, you can divide this, and like this way it will continue until you are obtaining your required solution. So, basic idea is this thing. So, this in terms of the algorithm, we can write it like this: branch and bound algorithm. If required, optimal integer solution of the problem can be automatically satisfied without imposing the integer restriction in the LPP. In that case, stop. That means, without imposing integer restriction, if I solve the problem and if I obtain that the solution is optimal and providing me the integer solution, in that case that solution will be the optimal one and I will stop. Otherwise, I will go to the next step. Whatever we have told, out of non-integer xj's, j belongs to I, 1 to n or whatever it may be, choose one particular xj and rewrite it in the form of xj equals wj plus fj, where wj is the integer part and fj is the fractional part of this xj, and obviously your fj lies between 0 and 1. So, in that case, after that, in step 3, any feasible integer solution of the problem which will satisfy either xj less than equals wj or xj greater than equals wj plus 1. So, if we add these two conditions in the problem, we will obtain two subproblems. Both subproblem you have to solve and following observations can be made. Both subproblems, whenever we are solving, the observations can be made. A, if the solutions are integer valued for both subproblems, if the solutions are integer valued for both subproblem, choose that subproblem having larger objective function value as required optimal solution. So, please note this one: if the solutions are integer valued for both subproblems, choose the subproblem having larger objective function value as required optimal solution. So, this is one case which may arise. The next case will be, if the subproblem gives no feasible solution, then select another non-integer decision variable in the basis, another non-integer variable, and proceed as step 2 whatever we told. Means, if the non-integer variable which you have taken, after that you are dividing it into two subproblems, and if both the subproblems having no feasible solution, then you have to choose another non-integer variable and repeat the process 2 as we are saying as in step 2. If number C, if the solution is not feasible integer solution, repeat the process of step 2 as on the constraint set. That means, again follow the same process, subdivide the problem. When all possibilities exhausted, the algorithm will terminate. That means, it has no solution. So, this algorithm generates a tree form of solution set. Please note this one. As I have shown earlier, it will have a root. From the root, it will have some branches. Each branch may have sub branches. Like this way, it will continue. So, this algorithm generates a tree form of the solution set. Each non-terminating node will have 2 branches which will be issued from here. That means, from root there will be always 2 branches. Now, let us take one example and let us see how the branch and bound method exactly works for this particular problem. Let us take this problem. Maximize z equals 2x1 plus 3x2 subject to 5x1 plus 7x2 less than equals 35, 4x1 plus 9x2 less than equals 36 and x1 x2 greater than equals 0 and both are integer. Now, for this problem I can find the solution in 2 ways. One is I can use the normal simplex method, I can add the slack variables on it, and if I wish then I can write down the initial simplex method, initial simplex table, and from there I can go on iterating until I am obtaining the solution. Instead of doing the simplex algorithm, since it is a problem of 2 variables only, we will use the graphical method with respect to this one. So, you see these 2 problems, these 2 constants. For the graphical method, what I have to do? I have to draw the line for 5x1 plus 7x2 equals 35 and 4x1 plus 9x2 equals 36 and x1 x2 greater than equals 0 and they were integers. So, please see from here that in this line represents 5x1 plus 7x2 less than equals 35, that is equals 35. It crosses the point 7 on the x axis and 5 on the y axis, whereas 4x1 plus 9x2 equals 36. This will meet the point at 9 on the x axis and 4 on the y axis. So, you are getting the second line 4x1 plus 9x2 less than equals 36. Since they are both less than equals, direction will be for both of them will be this one. So, and the region will be this shaded region bounded by these 2 lines and the coordinate axis, that is x axis and y axis. So, from the graphical solution it is quite obvious these are the extreme points, and if you calculate you will obtain the maximum value of this at this point, that is 63 by 17 and 40 by 17. Therefore, after graphical solution of the original problem, what we are obtaining? X1 equals 63 by 17, X2 star is 40 by 17 and Z star equals 246 by 17. So, using this graphical method, what happens? Your solution is like this: X1 star equals 63 by 17, your X2 star equals 40 by 17 and your Z star or Z max is becoming 246 by 17. Although this is the optimal, the solution which you obtained, but this solution is not feasible, since both of them x1 and x2 are non-integer. Now, so since both x1 and x2 are non-integer, so I have to choose any one of these two. So, we are choosing, say, choose x1. We are choosing x1 because x1 has the largest fractional value, So, what is the upper bound of z? Initial upper bound of z is initial upper bound of z. This is equals to 246 by 17, which is approximately, if I make, this will be 14 point this. Now, similarly, the bound of x, initial lower bound of x is from 3 to 4 from here. Your x is 3 point something. So, x can take x, not x, but the bound of x1, if I have to write bound of x1 is 3 and 4. This I got from this value 63 by 17. This is 3 point something. So, lower bound of x1 is 3 and upper bound of x1 is 4. Similarly, lower bound of x2 will be 2 and in the same case this is 34. So, lower bound of x2 is 2 and upper bound of x3 is 3. So, we are finding for the integer, for the variables which contains non-integer values, what is the lower bound and what is the upper bound. So, for x1 lower bound is 3 and upper bound is 4. So, from here now I can formulate two problems. In one case your x1 will lie in between 0 to 3, in other case your x1 will be greater than equals 4. So, now this original problem, say this was your SP, what we denote this thing as SP. So, your SP, this problem is divided into two subproblems which we are denoting as SP1 and SP2. Your SP1 will be maximize Z equals 2x1 plus 3x2 subject to 5x1 plus 7x2 less than equals 35, 4x1 plus 9x2 less than equals 36 and 0 less than equals x1 less than equals 3. This extra condition now we are adding compared to the earlier problem, if you see, and this we are adding since the lower bound is 3 and upper bound is 4 for the variable x1. So, x1 lies between 0 to 3, x1 x2 greater than equals 0 and obviously they are integers. And similarly, your problem 2 will be SP2 will be maximize Z equals 2x1 plus 3x2 subject to 5x1 plus 7x2 less than equals 35. First two constants will remain same, that is second one will be 4x1 plus 9x2 less than equals 36, x1 greater than equals 4, x2 greater than equals 0 and both the variables should be integers. So, now what you have to do? So, you see the original problem I am dividing into two subproblem, and how we are dividing it? We are dividing it on the basis of the value of the lower bound and upper bound of the non-integer variable. So, in the basis or in the solution, if I have the variables whose values are non-integer, from there I will choose the variable which has more or larger fractional value. As in this particular example, we have chosen x1. Since x1 has the larger fractional value, then we are finding out the lower bound and upper bound of x1, which is 3 and 4 respectively for this particular problem. Then we are creating two subproblems. Now, these two subproblems again can be solved by graphical method. Purposefully we have chosen it. So, for the first subproblem, if you choose, then your problem will be like this. Your one is 4x1 plus 9x2 equals 36, another line 5x1 plus 7x2 equals 35 and x1 less than equals 3. This is the bound. So, this is on this direction. So, your feasible region is the shaded one, and if you calculate, you will find at the point 3 8 by 3 you are obtaining the solution. So, therefore, your solution is for the first problem x1 equals 3, x2 is 8 by 3 and z star equals 14. So, please note this one, that for this problem your x1 star this is equals to 3, your x2 star is 8 by 3 for the first problem SP1 and your z star is 14. 8 by 3 and your z star is equals to 14, whatever you are getting. Now, similarly, for the second problem also graphically I can find out the solution. My solution set will be like this. This is the line again 5x1 plus 7x2 and this is the line for 4x1 plus 9x2 less than equals 36 and for this case your x1 is greater than equals 4. If you try to find out the solution, you will get it at this point, the maximum value. So, for this case your solution is x1 is 4, x2 is 15 by 7, z star you will obtain 101 by 7. So, you are getting these two. So, for this case your solution is x1 star equals 4, x2 star this is equals 15 by 7 and z star equals 101 by 7. So, if you see in this case for this problem I obtained two solutions, but in both cases your x2 is having non-integer value and your for the problem SP2 basically you have more optimum value of the objective function. So, as we have told, since in both the cases I am getting non-integer solution, again I have to subdivide the problem now. Since I have to subdivide the problem, that means now your SP2 has to be subdivided into SP3 and SP4, these two. Here if you see your x2 is the non-integer value, the lower bound and upper bound from here it is very clear, lower bound of x2 will be 2 and upper bound of x2 will be 3. So, in the original problem, from the original problem means I want to say on this particular problem now I will impose one more condition now. What will be the condition? So, SP2 I am dividing. So, this constraints will remain as it is. Along with this I will add one more constraint for x2 for the lower bound and for the upper bound. Lower bound is 2 and upper bound is 3 for this case. So, your I can write down your SP3 as maximize z equals 2x1 plus 3x2 subject to 5x1 plus 7x2 less than equals 35, 4x1 plus 9x2 less than equals 36. Your condition was x1 already greater than equals 4, that means one condition will be x1 lies between 0 to 4, 0 less than x1 less than equals 4, it cannot be this one, and the one more condition now I will add, that is 0 less than equals x2 less than equals 2. So, whatever was there along with this your x1 must lie in between now 0 to 4, at 4 we obtained the solution. So, x2 lower bound is 2, upper bound is 3, for that reason here I have added x1 x2 lies between 0 to 2 and x1 x2 should be integer. Similarly, your SP4 this will become now this is SP4. So, SP4 will be maximize z equals 2x1 plus 3x2 subject to 5x1 plus 7x2 less than equals 35, 4x1 plus 9x2 less than equals 36. Your this condition is there, that is x1 lies between 0 to 4 and your upper bound, if you see here, upper bound is 3 since it is fractional part and upper bound is 3. So, therefore, I have to add one more thing x 2 greater than equals 3 and these are the all are integer values. So, now as we have done earlier, graphically I will solve this problem. So, I am just seeing here that this is the line 5 x 1 plus 7 x 2 equals 35. This is the line 4 x 1 plus 9 x 2 equals 36 and this is the line x 1 less than equals 4, that is this thing, and what was the other one, x 2 less than equals 2. X 2 less than equals 2 was the second one. If you see, x 2 lies between 0 to 2. So, that your solution space will be this one. This shaded region is the feasible region and if you calculate, you will find at the point 4 2 we are getting the maximum value. So, your solution in this case will be x 1 equals 4, x 2 equals 2 and z star equals 4. So, for this problem your solution then becomes x 1 star equals 4, x 2 star equals 2 and your z star equals 14 from the problem. Similarly, now I can find the solution of this one. For this case, if you find your 5 x 1 plus 7 x 2 equals 35, your 4 x 1 plus 9 x 2 equals 36, x 1 less than equals 4. You see the directions for this also, direction is this, for this that means this area, but x 2 is greater than equals 3. That means this portion, upper portion. So, therefore, they are not intersecting anywhere, or in other sense we can tell that this problem has no feasible solution and z star does not exist over here for this problem. Graphically it is quite clear. Just see, there will be no intersecting area among these 5 coordinate axes and these 4 lines. So, for this case we can write down no feasible solution. For this problem, no feasible solution. But for this case you see, we obtained the optimal solution and they are satisfying the integer restriction also. Therefore, the solution of the original problem will be this one, x 1 equals 4, x 2 equals 3, 2 and z star equals 14. So, the original solution for this problem will be the solution of SP3, which is x 1 star equals 4, x 2 star equals 2 and z star equals 3. So, I hope it is clear that how using branch and bound method we can solve one integer programming problem, where basically whenever in a solution you are obtaining non-integer value for a decision variable, you are breaking the problem into 2 subproblems. In one subproblem, you are adding one more constant for the lower bound of the non-integer variable. In another subproblem, you are breaking it into, you are adding the constant of upper bound, and by this way again you are solving the problem and you are repeating the process until you are obtaining the desired solution.